Okay, folks, last video of this module. This should be a fairly short one. We're just going to review some of the properties of the Maxwell-Boltzmann distribution of speeds and make sure that we know what are the appropriate units to use in this equation. So I added one extra slide here under the 1.5 learning goal because I realized I ran out of space. And I wanted to include a little bit about units. So let's rewrite that equation that we came up with. Okay, f of v equals 4 pi times, and remember our constant k went m over 2 pi times k Boltzmann times t all to the 3/2 power times velocity squared times the exponential of negative mv squared over, that's 2 times kbt, all raised to that exponential. But I think that's a redundant parenthesis. Yes, I don't need them. Let me make sure that I got that written all correctly. Okay, so let's talk about units. Okay, so this little m that I was writing here, I wrote that as a lowercase m. We want to start getting used to seeing that in this class. And when I write that lowercase m, let's actually change this to red so we can really make it stand out. That lowercase m specifically has units of kilograms per single molecule, which is why it's paired up with Boltzmann's constant, okay? Because remember, Boltzmann's constant, Kb, is technically joules per Kelvin per molecule. So now we could also rewrite this equation using a different set of units. So we could use big M in place of little m. And that in this class, that big M will have units of kilograms per mole. And thus, if we see a big M, we have to pair it up with gas constant R, because remember, that's got units of joules per Kelvin per mole. Okay, so we could use this expression with R, or we could use this expression with Kb. But we have to remember, if we use it with Kb, we're going to use that little m, which is kilogram per single molecule. If we use this expression with big capital M, the molar mass expressed in kilograms, then we've got to pair it up with R, the gas constant, 8.314 joule per Kelvin per mole. Okay, so let's make sure that we keep track of that in our units. Okay, so here is what the equation looks like. So it looks like the same Boltzmann distribution we showed before. Except for now, I'm going to actually skip one slide, apologies. You can see we've got speed on the x-axis, and that's going to have units of meters per second. And we've got fractions of molecules on the y-axis. So if we were to integrate the area under any one of these curves, so in other words, the integral from negative infinity to positive infinity of f of v dv, remember that equals 1, or 100% of our population. So we can calculate single individual values by looking at, one individual velocity, let's say, right? Like, let's say we go to that velocity, and then we can say, what is the fraction of molecules with that specific velocity? So there's 3 different ways that we can do this, because our curve here is not a symmetrical curve. It's weighted. So that gives us a couple of different ways of averaging this. We can average it with the most probable speed. And so that is typically given as a C star. And you can see that right there. The most probable speed is right on top of the distribution. And if you recall, we can find that by taking f prime of v, so taking the first derivative, set equal to 0, and solve for v. Okay, so when we do that, we get the following equation: 2RT over big M square root, or we could write that as 2 kBt over little m square root. Either one of those is okay and will give us a unit in meters per second. We could calculate the RMS speed, that's the root mean square. And you can see the root mean square appears right there. It's a little bit above a higher velocity than the most probable. RMS is a useful quantity in physics for reasons we'll uncover throughout the semester. And the RMS speed, it's the root mean square. So we take the square, okay? We take the mean of that square. So that's what those brackets symbolize. And then we take the root. So root mean square. And so the way that that is calculated in mathematics is the following. I'm going to get a big bracket. We're going to integrate, and technically we can just integrate this from 0 to infinity because we don't have any negative velocities. And now the calculation that we perform is v squared times f of v times dv, and all to the 1/2 power. So calculating the mean of an integral is done in a very similar way. So we can see now the mean speed, which is given by c bar. And the mean speed is very close to the most probable. So that was c star for the most probable. C gives me the RMS, and c bar gives me the mean. So you can see they're all pretty similar, and they're not identical, again, because this is not a symmetrical distribution. So to calculate the mean, it's just, that's the symbol, okay? Typically, we see that written as c bar. And now that's the integral from 0 to infinity of just v f of v dv. So you can see here in our RMS, our root mean square calculation versus our mean calculation, we've got that integral v f of v for the mean, or v squared f of v for the mean square. And then taking the square root of that is what makes it the root mean. And then for the mean, we don't have to take the square root of that because it's just the mean. Okay. So all of these will give us slightly different values. And if we keep looking at these equations here, my RMS becomes 3RT over big M square root, or 3 kBt over little m square root. And then my mean speed is 8 RT over big M, oops, and there's a pi out there, square root, or 8 kBt over pi little m square root. So I'm not going to go through these full derivations, but I may ask you to do that on an exam or an assignment. Hint, hint, wink, wink. Okay, so now if we continue along on this slide, if we look at what happens here as a function of temperature, right? Because remember, kind of the point of this was to look at the distribution of speeds as temperature changes. So we can see as things get hotter, the distribution gets more wide, so we're populating more translational states with higher temperature. And not only are we populating more of them, but the population is spreading out. And if we look at where the most probable was indicated, that's what these dotted lines show. We can see overall our molecules get faster as they get hotter, which is what we kind of expected from our intro level courses. Conversely, if we look at the same temperature, but now different masses, you can see the lighter masses are faster for a given temperature, and the heavier masses are slower for a given temperature. And that's all good, happy, feel good physics and chemistry that hopefully we remember talking about in our intro courses as well. So again, as molecules, and specifically as gas phase molecules, get hotter, their speeds get larger and more spread out. As these gas molecules get more massive, their speeds become less and more well-defined, or the distribution becomes tighter. Okay, and we'll explore this a lot more detail in our Friday computer lab session. Okay, folks, that's it for Module 1. I'll see you in the next one.